X-rays are produced when electrons travel from the cathode filaments and interact with atoms in the anode target. This movement of electrons is what we can call the tube current. Tube current is measured in units of milliamperes, which is abbreviated mA. So tube current is simply the movement or flow of electrons in the X-ray tube. The tube current is actually very similar to a current of water flowing down a river. A current is just the flow of water. If we have a large current of water, that just means there's a higher flow rate of water moving down the river. If we have a small current of water, that just means we have a lower flow rate of water moving down the river. In the same way, tube current just refers to the flow rate of electrons moving through the X-ray tube. So here's how those relationships work. If we increase the mA, that's the milliamperage, at the control console, this results in an increase in the tube current, which is simply an increase in the rate of electrons flowing through the tube. And this, in the end, increases the total number of X-rays produced. Conversely, if we decrease the mA at the control console, this decreases the tube current, which is, by definition, a decrease in the rate of electrons flowing through the X-ray tube. And this finally decreases the number of X-rays produced. The process of creating the X-ray tube current starts at the cathode filament. Setting the mA at the control panel is the primary factor controlling the amperage applied to the filament. As we increase the mA, this increases the filament amperage, which increases thermionic emission, increasing the number of electrons created, which are then available to flow across the X-ray tube and collide with the anode, creating X-rays. So tube current actually starts with thermionic emission and the filament current. Tube current, which is defined in units of milliamperes, or mA, affects several important aspects of the X-ray exposure. If we increase the mA, this increases the X-ray beam intensity as the total number of X-rays in the beam, and the relationship is proportional. For example, if we increase the mA by double, the number of X-ray photons in the beam, that's the intensity, will also double. Obviously, the reverse is also true. If we decrease the mA by half, then the number of X-ray photons produced, that's the beam intensity, will also decrease by half. Tube current, or the mA, also affects the receptor exposure in the exact same way that it affects intensity. If we increase the mA, the receptor exposure also increases by the same amount. So if we double the mA, the number of X-rays striking the receptor, that's the receptor exposure, will also double. And of course, the opposite is true. If we decrease the mA, this decreases the intensity and the receptor exposure by the same factor. Changes in mA also have the same simple relationship with patient dose. If the mA is increased, the patient dose will increase proportionally. That just means by the same factor. Of course, all of these relationships assume that only the mA is changing and all other factors remain the same. The mA has important relationships with other exposure factors, especially exposure time. The exposure time refers to the amount of time that the X-ray tube is on and X-rays are being created. The product of the mA and exposure time in seconds is called the mass. The mass is an important factor influencing the intensity, that's the quantity, of the X-ray beam. Usually an operator sets the mass rather than setting the mA and time separately. There's a reciprocal relationship between mA and time. This means that multiple mA and exposure time settings result in the same total mass and therefore the same total beam intensity. For example, 50 mA times 0.20 seconds equals 10 mass, but 100 mA times 0.10 seconds also equals 10 mass. And finally, 200 mA times 0.05 seconds still